Now there are few things for all those people who are not used to this platform. Just try and understand what I am trying to tell you. Okay? See, when I say something, there is a lag of around a minute and a half in what I am saying and what you are listening. So when you are listening, I have already gone past around a minute and a half. So when you listen to something and then you type your query, then I read that query and I will, whenever I will respond, then you will listen to that after 1.5 minutes. So there is always a lag. So once you type your query, then wait, I will read it, then I will discuss it, but you will get to know about it about a minute and a half later. So there is a lag. I'm clarifying certain things. There is a lag of a minute. Okay. Second thing is that whenever you are asking me a doubt, you have to understand I can't see your faces. I can only read you as a chat, right? So you have to ask complete questions. Whatever is in your mind, you have to make a complete sentence out of it. Don't just write one word and give a question mark. Understand? Because I don't know what part of my discussion you have listened to and what the doubt has arrived. So you have to write complete question. Third is, most of the things are planned in a way that as we move ahead in the lecture, things get starting to clarify. At the end of every major topic, I am going to give you time to ask doubts. I would prefer if you wait till that time. If your doubt has not been cleared, then only ask doubts. So ask doubts at the end of a topic. This will save not only my time but your time as well, because we have got a limited window. We have got about 1.5 to 2 hours that I have planned for you. I know you guys are busy during the week and you guys are tired in the evening. I hope you had dinner. So we are going to make it very crisp and very, very high yield, right? So let's start with gas laws. Now this is a topic called as physics in anesthesia, and physics is a very, very important part of anesthesia. Later on you will also realize that chemistry is also a very important part of anesthesia, but physics in anesthesia is very important because all the principles of physics are utilized in the conduct of anesthesia, handling of gases, as well as later on in the monitoring. So let's first start with a very basic thing that will help you later on also, that is pressure conversions. This is something very commonly asked. How do you convert different units of pressure? So there are many units in which pressure are defined. Pressure is force upon area. Force upon area. Normally, atmospheric pressure is defined as the standard of the pressure, and 1 atmospheric pressure is considered to be 760 millimeters of mercury, that is 1030 centimeters of water, which is 14.7 psi. What is psi? Pound per square inch. psi is pound per square inch. All right. This is the conversion that will help you, that if you get a numerical based question and if suppose they have given atmospheric pressure or they have given centimeters of water, then how to convert it into psi or kilopascal or mm of Hg, right? Now let's first try and understand a basic difference between a gas and a vapor. A gas and a vapor. Do you guys know the difference between a gas and a vapor? Have you ever thought about what is the difference between a gas and a vapor? So to understand this difference, let's first understand the concept of critical temperature. Critical temperature. Now what is a critical temperature? Critical temperature is the temperature above which a gas can't be converted into liquid form. See, whenever you compress a liquid, a gas, the molecules are going to come closer together. When you compress and the molecules come closer together, at some point there will be a cohesive force in the molecules and the state of that particular gas will convert into liquid. That happens under pressure. But every gas has a temperature above which no matter how much pressure you apply, the gas will never convert into a liquid form. That temperature is called as critical temperature. So you define a gas where the critical temperature is above room temperature. Critical temperature is, below room temperature. So this will always be in a gaseous state at room temperature. Example, oxygen has a critical temperature of 119 degrees Celsius. Room temperature is 20 degrees Celsius. So at room temperature, oxygen will always be above its critical temperature. And therefore, no matter how much pressure you apply, it will always be in gaseous state. So it is a pure gas. But any agent whose critical temperature is above room temperature, then this can be converted into a liquid. So it will be called as a vapor. Example, nitrous oxide with a critical temperature of 36.5 degrees Celsius. 36.5 degree Celsius. So now what will happen at room temperature of 20 degrees Celsius? The temperature is below the critical temperature, so it will be in a liquid form. But only when you start boiling or the temperature rises will it get converted into gas, right? So then it will be in a vapor. Vapor means there will be a liquid, and above that liquid there will be a gaseous state called as a vapor. So you have to understand the difference between a pure gas and a volatile vapor. All right. Keeping this in mind, let's first try and understand what all things we are going to cover in the gas laws. So we are going to cover these 9 gas laws today that are going to have some clinical implication as well. We are not just simply going to remember about physics or chemistry just because we want to, because it is all these laws will have some clinical implication. So this is a basic understanding of what we are going to discuss in the next 45 minutes. Avogadros law or hypothesis, Dalton's law of partial pressure, Boyle's law, Charles law, Gay-Lussac's law, these are called ideal gas laws, universal gas law, Henry's law of solubility, critical temperature we have already discussed, and its effect, pointing effect, we will discuss when we discuss the storage of gases and cylinder. Then we will discuss this pointing effect. We are going to in effect discuss these 7 laws right now. Okay, so let's start with what is an ideal gas. What is an ideal gas? So you have to define. All these laws are based on the concept of ideal gas. What is an ideal gas? Ideal gas is one that has a negligible volume. It follows the laws of Newton, follows Newton's laws. Follows Newton's laws. And there is no force between the molecules of a gas. There is no force between the molecules of the gas. These are the 3 things that define an ideal gas. Ideal gas. And whenever we talk about ideal gas, we also have to talk about ideal temperature and pressure, that is ideal surrounding. So standard temperature is 273 Kelvin or 0 degrees Celsius, and standard pressure is 1 atmosphere. We have seen 1 atmosphere is 760 mmHg, 1030 centimeters of water, 14.7 psi, and it is 101.3 kilopascal. That is the SI unit of pressure. This is the SI unit of pressure. Kelvin is the SI unit of temperature. I hope you are going back to your old days of physics and chemistry that you did in PMT, We have to actually go back to these things all over again when we are discussing these gas laws. Okay. I beg your pardon. I'm suffering from a very bad viral. It's just relentless cough. Everybody following me? Everybody is with me? You guys had dinner? You guys had dinner? Okay. Now let's start with first law. Avogadros law. Very simple. This is standard law. We have all discussed about it. What does this law state is? At constant temperature and pressure. At constant temperature and pressure. Okay, Ravina, Divya, you can munch something in between while you are listening to what I am saying. Okay. Even I had not had dinner. Normally I have my dinner at around 6:30, but today I was caught up in a lot of things. So even I am going to have my dinner after we are done with this class. Okay. So don't worry. I'm with you. So at constant temperature and pressure, equal volume of the gas will contain same number of particles. Either molecules or atoms. This is Avogadros law. This is Avogadros law. Equal volume will contain same number of particles. And these number of particles is called as Avogadros number, which is different from the law. But Avogadros number N is equal to 6.023 into 10 raised to the power 23. That is the standard number of molecules in 1 mole of a substance. In 1 mole of a substance. This is Avogadros law. If you have to write it in the equation form, then it will be V by N is equal to K, where V is the volume of the gas, N is the molar amount of the gas, and K is the constant. K is the constant. This is Avogadros law. Avogadros law. Now, what is the clinical implication of this Avogadros law? So let's understand it first. 1 mole of a substance will always carry 6.02 into 10 raised to the power 23 molecules. And 1 mole of a substance will always have a same volume, that is 22.4 liter. So if you are talking about isoflurane, the weight of isoflurane, 1 mole of isoflurane is 184 grams. So what does it say is 1 mole, 1 molecular mass is equal to volume 22.4 liter is equal to weight 184 grams of isoflurane. So there is a standardization. If there is a gas, then 1 molecule of gas will always occupy the same amount of volume, that is 22.4 liter, will always carry the same number of molecules, that is 6.023 into 10 raised to the power 23. What is the clinical implication? What is the clinical implication? So let's see what is the clinical implication. So we know molecular weight of isoflurane is 184 grams. That means 1 mole of isoflurane will contain 184 grams, which will occupy a volume of 22.4 liter. So suppose in a vaporizer, I have taken 0.1 mole of isoflurane, that is 18.4 grams of isoflurane. So how much volume will it occupy? 2.24 liters. Now if I want to create 1% concentration of isoflurane, then with how much volume of oxygen should I dilute it? Dilute with 224 liters of oxygen. So what will I get? I will get 1% isoflurane. Because 2.24 liter will be the volume of isoflurane. When it gets diluted in 224 liters of oxygen, then the concentration of isoflurane in that particular gas mixture would become 1%. That is how, when we change the dials of vaporizer, we can change the concentration of the agent that is being delivered, right? We will discuss all these things in detail again when we will discuss vaporizers. All right. This is the implication of Avogadros law. See, 18.4 ml of isoflurane will occupy a volume of 2.24 liters. So if I want to make 1%, I will dilute with 224 liter. If I want to make 10%, I will dilute with 22.4 liter. This is the implication of Avogadros law. Avogadros law. Equal volumes will contain equal number of molecules. Okay. Second is Dalton's law of partial pressure. This is something that you already know. In a mixture of gases, total pressure of the mixture is equal to sum of individual pressures. Individual partial pressures. So this can be very well written with P total is equal to P1 plus P2 plus P3 and so on. This is Dalton's law of partial pressure. So whenever you have a mixture of gases, then the total pressure is equal to sum of all the partial pressures of individual gases, right? Now let's try and understand its implication. Very important implication, right? Suppose at 1 atmosphere, you are breathing air, then how much is the alveolar oxygen that you are expecting, PaO2? So how much you will expect FiO2, fraction of inspired oxygen, into atmospheric pressure, right? 21% into 1 atmospheric pressure, that is 21.2 kilopascal. So what you expect is that somebody is breathing air, then at alveoli you should get 21.2 kilopascal. But when we are breathing air, then do we only take oxygen with it? No. There is also at the level of alveoli, there is CO2 that is getting exhaled from the blood. At the same time, when you breathe in, the air passes through the upper respiratory tract, nasal, the nasal spaces, the oral spaces, and it gets humidified, right? Will that have an impact on the partial pressure of oxygen? Yes, because now there is another gas that has been added. So at the level of alveoli, PaCO2 is considered to be 5 kilopascal, and a saturated water vapor pressure is considered to be 6.3 kilopascal. Now if you calculate PaO2, then what will it become? FiO2 multiplied by P total, that is atmospheric pressure, minus P water vapor minus PaCO2. Now it will become 0.21, that is 21%, into 101 minus 6.3 minus 5, This turns out to be 14.9 kilopascal. This is the effect of humidification and CO2. So even if you are giving a higher concentration of oxygen at the alveolar level, the concentration, the partial pressure decreases. Why? Because of other gases. This is the implication of Dalton's law of partial pressure. Dalton's law of partial pressure.